Come on.
Hello, laser geeks. Today we are going to experiment with brass. Going to attempt to laser weld 1/8 inch bras flat bars with silicon bronze filler wire. Laser brazing with silicon bronze on brass results in surface wetting, not fusion. The laser energy melts the filler, but the brass base stays solid, no metallurgical continuity. The result is a cosmetic overlay, not a structural joint. Silicon bronze melts and flows, but unless the base metal also melts, there's no fusion.
I set the unit 340 watts modulated power. Let's go over here. Oops. Let me see it. Alright. My lockout was normally open, so what I do. So obviously 340, it's not enough. It just barely melts my filler metal, which is silicon bronze. I'm gonna go 460 now. Put another bit right next to it. Actually on this side. A little bit better, but not perfect. And my wire is tracking a little bit to the right. How can I fix that? Okay, I hope I did. Now I'm gonna do 520. Again, next to this guy over here. Okay. Let me zoom in a little bit. I have to move this guy. When I zoom in. Okay. So, where is my pointing wire? Oh, where did I put it? Oh, there it is. So over here, I'm testing. I'm starting at the low point and keep stepping up. So 300 power range. The wire barely melts. Okay, so kind of just glued it to the surface. Now the next one was a little bit over 400. Same results, but my wire tracked a little bit on the wrong side, on the right. So I blasted the base material, melted the wire a little bit, but just not enough. Then I stepped it up to 540, 60 range, somewhere around there. Adjusted the wire a little bit. It's a little bit better, but I don't want to clamp it off. I'm gonna take it up later. So I don't know if it's visible over here. There is a line. What is it? It's a bunch of pinholes punching into the material and boiling up the zinc. Exactly, that's going on. So I'm gonna do another thing. I'm gonna lower my scan, make it a little bit less, shorter. I think I'm around, I have to check my settings, but I think around 1.5 millimeter, maybe 2 millimeters, somewhere in that range. I have to go down to around 1 millimeter range. And I'm gonna power up to 640. And I'm gonna do another bead over here, we're gonna check it. And if it seems to be alright, then I'm gonna hit it. But I know the outcome. So basically it's gonna melt the two pieces of material on the surface. It's gonna have almost zero penetration. And Then we're gonna do it on the other side as well, and we're gonna break it up. So it's gonna be somewhat strong. How strong? Let's say if you have some appliances and it's just for visual, you could do this, and then you can grind off the excess, and you still have a 0.5 millimeter filler metal flow into your gaps. I don't think more. Same thing from the other side in that case. So basically you end up approximately 1 millimeter fusion and 2 millimeter gap, because it's a 3 millimeter material. So what I'm doing, 640, and I'm gonna make the scan a little bit less.
Why? It's a range, not a point. As an alloy, silicon bronze melts over a range due to the varied atomic bonding forces between its constituents. The solidus marks the start of melting, and the liquidus marks full liquefaction. Higher silicon or zinc content can shift this range slightly lower. Running 640 watt range modulated power settings at a 60 micron beam. The problem is the 60 micron beam in this particular challenge. If my unit were over 150 microns, it would make the task easier. The reason is that the smaller beam acts like a search and destroy pattern on the zinc elements in the metal lattice, which is why the backside shows a large number of pinholes. That's why it behaves like a band-aid cap on brass cosmetic, not structural. Base composition: to 95% copper, to 3% silicon. Trace elements: zinc, tin, manganese, iron. Melting range: 850 degrees Celsius to 890 degrees Celsius is the typical melting interval. The presence of silicon lowers the melting point compared to pure copper, 1085 degrees Celsius, improving castability and fluidity. When used on brass, overheating can cause zinc boil-off from the base metal, leading to porosity and toxic fumes, especially if brass is pushed near its liquidus to 930 degrees Celsius. Silicon bronze melts and flows, but unless the base metal also melts, there's no fusion. That's why it behaves like a band-aid cap on brass cosmetic, not structural.
For visual,
the filler metal melted all
doesn't look
right,
that bad,
but the base material did not. It has a slight fusion, but not as much as we would expect when welding.
But it's not good. I'm gonna do another one over here. Alright, so now we're gonna go to the center, but I wanna make it flat, sort of. Okay.
Interesting. It did hold a little better than I expected, but it took less force than my Coke can demo test.
See how it's shooting through? I know already the outcome. I have done this a couple of times. I'm gonna flip it. And I already know my settings as well, but I had to show you guys. Now, what do you see over here? Look at the blow through. So this was the edge that I told you about, and same thing over here. What's happening over here, it's kind of search and destroy the zinc elements in the brass. Do you remember this? $300, nothing happening over here. Okay. This was 640. Look at the other side. We got a little blow through at the beginning because my wire was not in the laser beam. But again, I don't know how much visible, but there is a line, it's also blow through. Okay, so basically there is a weak material over there. There is holes. So if we could put a pressure on it, water or gas, everything goes through. It's like a sieve. Same thing over here, that's even more visible. Over here, obviously, because we have a gap. And now, I'm gonna clamp it down. It's quite hot, by the way. Okay, I'm gonna brush it a little bit. There we go. Put this tool away. I'm gonna put another bead over here. I'm sure in the camera you guys can see when the laser is going through, it's hitting my table somewhere around here. If you guys remember, I mean whoever watched the other videos, so the scan enters the material, right? And bouncing off of the side, and so it goes through shallow and goes through. Same thing happened, and beams ending up hitting my table right here, and I was welding over here. So most likely I was a little bit off angle, my gun a little bit like so. And that's how it went there. But it's not relevant now. Okay. I don't know if you guys see it, but it's not really any fusion in the center. It has melts, but no fusion. And on this side, give me a second.
Laser welders are typically focused in the 150 to 25 micron range. The 25 micron spot size is a newer development, now being integrated into advanced systems. It acts like a search and destroy mission on zinc atoms and brass. The zinc boils almost immediately, and overheating drives zinc boil off from the base metal. That leads to porosity in the joint and toxic fumes, especially near brass's liquidus, to 930 degrees Celsius. Silicon bronze filler wire melts 30-60 degrees Celsius below brass. But unless the base metal also melts, there's no fusion.
Okay, so I'm gonna do one clamp, okay, and no wire. See what's happening? Almost everything going through, and my power is still the same. I did not change anything. That much difference the wire makes. Look, other side. Where is mine? Here. It accidentally hit one of the welds, so let's do this. I'm gonna run something over here. Again, same thing. And when we flip it, there is nothing over there, so clear area. Because I don't want to touch it, it's hot. And also, it's a good hand rest. So, flip it. See the other side? Now, you could put your finger on. It's like a sandpaper. One, I don't know how many holes, extreme amount of holes. And basically we did not melt the brass itself, well, sort of. We blow all the zinc elements out of the brass in this area. and whatever is remaining is pretty much copper and trace elements, nothing else. Okay. So I'm gonna move this a little bit over here, and we go here. I'm gonna raise the power. Not significantly, just like 840 range, let's say. 840. And look. See? Again, it's a bunch of little pinholes. And you could see on each side, left and right, where the laser beam is dwelling for how many? About 50 hertz wobble. Okay. And obviously the two sides, when the wobble comes back, it spends a little more time, so it has a little more dwelling time on each side, and that's what you can see on the camera, the pinholes. So one side and the other side, the edges of the wobble. Now I'm gonna set the wobble even less, a little bit. Let's redo this experiment. Again, go back this side. By the way, you can see over here it went through one of these guys and burned into the aluminum. Okay, same power, but oops, bring it up. Same power, but I string the wobble even more. Right there. Here. Okay. So once again, the same result, just the wobble is skinnier. Okay. So I'm gonna cut this somewhere, and we're gonna re-weld it. You see how it's gonna align better, something like this. And I'm gonna bring it. We're gonna stay here. Alright. It's over here. Try to align as good as possible. Hold on, wait a minute. Oh, it's alright. I should have grind the edges as well, I didn't. So we ended up with a little larger gap. It's horribly big, especially for the brass. This is extremely large gap. So what is the difference right now? The steel and modulator power. I'm going to lower the scan, and I'm going to run a test before we're going to weld it. 840, significantly higher, but our scan width is significantly less. Let's do it. In my opinion, this power is extreme amount, too much, way too much. I'm going to back it up to 760. Let's make another test somewhere over here. You can see the blow through coming. This one is too much. See? Way too much. I'm gonna go back to the 600 inch. Actually 620. Over here another test, 620 range. I think it's better. It's still blowing through, but it doesn't cause so much damage. So when a lot of laser beams coming through, you're making more damage than good. So theoretically the 620 is still too much, but if I go any lower, it doesn't want to melt the filler material. Much better, because barely some laser beams went through. I didn't go all the way. So now one side is going to be enough to clamp. Okay, almost perfectly aligned. All right, can put it away now. I'm gonna clean it with the grinder. Where's my grinder? Here. Okay, this side. So, if it would be horribly wrong, this whole test, it would already separated. But it's not. So I was able to melting my filler metal into the hole. Oops, sorry. So I was able to melt this. As you can see, when I grind it up, we have this a little bit more than a millimeter wide color differentiation, and right next to it, I don't know, better if I put this down over here. I don't know if it's gonna be visible or not, but right next to it, especially, goddamn, in this section over here, there the pinholes present right here. The same effect what we have over here, just much smaller. So what does it tell me? What it tells me, I have to lower my wobble even less what I have right now. Because the wider I go, the more of a pinholes I'm gonna have. Okay. So it doesn't look that bad, but should I break it? Or what should we do? No, I'm gonna cut this again somewhere over here. We're gonna do the same thing. I'm gonna shrink my wobble. I'm gonna turn this because I want to have a flat surface to clamp. Okay, this is quite flat, so you can go anywhere. Also a little bit around the edges as well. Okay, so it's almost 100% flat. Alright, so wobble. Like that. 620. 620. Okay. Right. Again, modulated power. Look for it on your own welding rig. Go this side. And once again, I'm gonna grind it. Once again, I'm gonna grind it. Let me see if I have a. Yes, I have. Finer. I removed quite a lot of material already. Ay, it's hot. Trust me. Okay, I'll find that even finer. Yeah. There you go. All right. It's hot. So after sanding, okay, let me try to get it at focus. I don't know if you guys can see what I see. It's pretty much, I've lost track as well. But what I'm gonna do, I'm gonna share a picture with my phone. Okay, so here clearly visible. So if I keep grinding, I think I'm gonna get to the point where it's gonna be no fusion. So see how much did I removed? We can test it that way. I'm gonna remove only one side, a little more. The grinder. I'm gonna put the 60 paper. I don't want to put a new because then it's gonna be way too much material removal at once. And right about now, no more filler metal. Vanished. 100% vanished. I'm gonna do one more flip, one more clamp. I just noticed with the 60 grit, it's easier to see the filler material and the base material right there. Now if I flip it, see that you can't find the trace of the filler metal anymore, and I removed not much. So how superficial it is. Now I'm gonna clamp it. Oops, not this one. One of these guys. Clamp. Actually, let's clamp closer. Clamp. See? It took a little power. And also you can see the base material start to bend as well. So it's not weak, very weak, but okay. So actually I'm gonna share a picture with my phone again, because on this brake there is clearly visible the original edges of the base material, and they shiny just as I grind it. Right there. So I'm gonna shot the picture when I do the video, and I'm gonna insert it. I think it's gonna be worth it. Okay. This is it for now.
Thanks for watching. If you enjoyed the content, please subscribe and give it a thumbs up. I appreciate your support. Got questions? Drop them in the comments. I'll do my best to answer. And if it's a big topic, we might even make a video about it.